Alright, so good afternoon, everyone. In the previous lecture, I gave you the introduction for the EM algorithm, right? Expectation and maximization algorithm. So we were discussing about the example in the discrete case for the EM algorithm. So we had this example, that two coin problem that we had. So scenario was like this. That we have, suppose we conduct the 5 experiment, and each experiment we toss a coin 10 times. All right, and the observed number of head and tails are given here. That is, under each experiment were given 5 head, 5 tail, 9 head, 1 tail, 8 head, 2 tail, 4 head, 6 tail, 7 head, 3 tail. All right, so here what we know, that the observed data are the counts of the head and tails. Here in this data set we have the number of heads and the number of tails here. However, we don't know which coin was used in each experiment. Okay, we had the two coins, and we flip each coin, means we flip the coins 10 times, okay, in one experiment, and recorded the number of head and tails, but we don't know in which experiment we used which coin. Okay, we don't know whether in the first experiment we used the coin A or coin B, or in second experiment we used the coin A or coin B. We don't know about that one. All right. So suppose here, now we are going to use some notations. So here, suppose coin A, here coin A with probability theta A. Theta A is the probability of occurring head for coin A, and coin B we are going to consider with probability theta B, where theta B is the probability of getting head through the coin B. So our goal is there to estimate the unknown parameters theta A and theta B. So our goal is here to estimate the unknown parameters, estimate the unknown parameters theta A and theta B. These both of them are unknown because we don't know that in which experiment we used which coin. If we don't know which coin was used in experiment A, how would we tell that what is the probability of success for coin A? All right, or getting head. And in experiment 2, what is the probability of getting heads of coin A or coin B? So we are not aware about it. All right, so this is the goal, to find out the value of theta A and theta B. So here we assume that, suppose, or let Hi is denoting the number of heads in experiment I, and Ni, suppose Ni is denoting the total number of flips, total number of flip in experiment I. All right. So how many times you were tossing in experiment I? That is your n. So in this example, this is basically ni equals to 10 for all I. All right. And how many times we are tossing? That is 5 times. So 5 experiments we are conducting. So it is 1 to up to 5. All right. So this problem is basically is not a standard problem of the binomial estimation. Okay, what we usually do in the binomial experiment, we just find out the probability of occurring total number of heads and total number of that one tails. So because the identity of the coin used in each experiment is basically hidden or unknown, so we cannot find out the value of theta A and theta B. All right. So to make this split, define a latent indicator variable here. All right. So for that one, we are going to define a latent indicator variable, say Zi. We are going to define the Zi here. Zi will be takes to value 1. Okay. When if experiment I, if in experiment I, coin A was used and 0 if in experiment I, coin B was used. All right, so this is the indicator function that we are going to assume here. Okay, so the variable Zi is not observed, so that's why this is a missing data or latent variable. And we are going to use the EM algorithm to find out it. So here I just explain why can't we use the standard MLE here. So before introducing EM, uh, it will be very useful for us to see what would happen if we knew the experiment, in which experiment which coin was used. So suppose for the example, we are going to consider that in experiment 1 and 4 we use the coin A, and in experiment 2, 3 and 5 we use the coin B. So easily we can find out the MLE of MLE of theta A and theta B. That would be how many parameters are there, how many heads was there, 5 and 4. So total 9 heads we were getting out of 20, total 20 flips. So that was 0.45. And for beta cap B, theta cap B, how many? 9, 8 and 7. So that is total 24 divided by 30. So it will be 0.8. So probability. All right. It would be like that. So if the assignments were known, so then each coin would simply have the binomial data associated with it. So the MLE of the binomial success probability was always that we already know that is P cap, basically total number of success or a total number of successes divided by total number of sorry total number of trials. All right. That is the basically formula. So from this formula, we computed the theta cap A and theta cap B. But here the problem is that in the present scenario, we don't know the which coin was used in which experiment. All right. So here, why MLE is difficult. So For each experiment, there are two possible hidden states we have, that is zi equals to 1 and zi equals to 0. All right. Since there are 5 experiments, so how many possible combinations of zi's are there? That will be 2 raised to the power. Okay, so it will be 2 raised to the power 5. So it will be 32 combinations. Okay, or possible assignments, total 32 assignments of the experiments to the coins are possible here. So for large number of experiments, the number of possible assignments will increase exponentially because will be in the power. All right. So making direct maximization of the observed data likelihood, it will computationally very difficult. So that's why we will move to the EM algorithm here. Okay. So in that case, in EM algorithm, we have the two steps. First is the E step, that is called as the expectation step. So we are going to compute the conditional expectation of the hidden variables given the observed data and the current parameter values. Okay. And then we have the M step, that is called as the maximization step. So here we are going to maximize that expectation. Okay, so maximize the expected complete data log likelihood with respect to the parameters. So, and we are going to repeat this algorithm till we are not going to converge it. All right. So the here we will assume that how we will develop the model. So here first we need to develop the model here. So here we need to assume that the conditional on the coin that is used basically, the number of heads in the experiment I follows the binomial distribution. Okay. So we are going to say that basically we should write assume that conditional on the coin used, the number of heads in experiment I, the number of heads in experiment I follows the binomial distribution. Okay. Definitely it will follow the binomial distribution. Yes or no? It will follow the binomial distribution or not. The number of heads in each experiment. Doesn't matter whatever the coin we are using. Okay. It doesn't matter which coin we are using. The number of heads will follow, total number of heads will follow the binomial distribution or not. Tell me. Yes or no? Right. So now, if experiment I, now consider if experiment I used coin A that we are supposing right now. Okay. Then what will be the PDF? Sorry, what will be the PMF? It will be probability of that HI, that is the total number of heads, given ZI equals to 1 for given theta A. Means theta is the probability of success or the probability of getting heads. Okay. for the coin A, it will be equals to Ni, whatever the total number of total number of flips of the coin is there, Hi, number of heads, okay, theta A raised to the power Hi into 1 minus theta A raised to the power Ni minus Hi. That will be the PMF of your experiment. Okay, for the experiment I, and for coin B, if coin B was used, so at that time it will be probability that Hi, given that Zi equals to 0, for theta B equals to Ni combination of Hi theta B raised to the power Hi, okay, 1 minus theta B raised to the power, whole raised to the power Ni minus Hi. All right. Now, suppose that for the simplification here, for simplification, assume that that a priori both coins are equally likely. Okay, means the chances of occurrence of any coin is similar. So at that time, what is the probability of indicator function? Taking the value of Zi equals to 1 will be equals to the probability of Zi equals to 0, means selecting the coin A and selecting the coin B both are equal. That is 1 by 2. For the simplification, we are assuming that one. It can be differ also. But right now we are considering this situation that both are equally likely, and selecting the probability of selecting each coin is 1 by 2. So now the likelihood function for the given data, okay. So because the coin identity is unknown, the probability of observing Hi heads is a mixture of two binomial distribution right now. Okay. So now because the identity of coin in experiment I is unknown, okay, so what will happen? The probability of observing Hi, probability of observing Hi heads is a mixture of two binomial distribution. Okay, it will be the mixture of two binomial distribution now. So what we are going to do here, so what will be the PDF at that time? PMF. So PMF will be probability of HI given theta A and theta B will be equals to probability of Zi equals to 1 into probability of Hi given Zi equals to 1 comma theta A for the given parameter theta A plus probability Zi equals to 0 into probability of Hi given that Zi means coin B is selected with parameter theta B. Okay, so that will be your mixture distribution of two binomial distribution. Okay, so it will be, what will be the PMF at that time? The PMF will be probability of Zi equals to 1 means coin A is selected, the probability is 1 by 2 into what is the PMF that we already know, that is Ni combination of Hi into theta A raised to the power Hi into 1 minus theta A raised to the power Ni minus Hi plus 1 by 2, because probability of Zi equals to 0 is also we assuming that 1 by 2 Ni combination of Hi theta B raised to the power Hi 1 minus theta B raised to the power Ni minus Hi. Alright, say it equation number 1 here. Alright, so here we need to assume the independence across the experiments, means the number of times when we were conducting the experiment, means experiment 1 is independent from experiment 2, experiment 2 is independent from experiment 3, 4, 5, 6, 4, 5, and so on, like that. All experiments are independent from each other. So assume experiments are independent, then the likelihood is L theta A comma theta B equals to product of I goes to 1 to M. Alright, M is basically equals to 5 because 5 experiments we had. So that will be 1 by 2 Ni combination of Ni and Hi theta A raised to the power Hi into 1 minus theta A raised to the power Ni minus Hi plus 1 by 2 combination of Ni and Hi into theta B raised to the power Hi into 1 minus theta B raised to the power Ni minus Hi. So this is your likelihood function. Okay. So this is find out the maximization of this likelihood directly. It is difficult. All right. So if the hidden indicator function Zi were known, so the complete data likelihood function would be simpler at that time. But For a single experiment, we can write it like this, that for a single experiment, we can write it like this, that probability of getting head HI for ZI for the given theta A and theta B, it will be 1 by 2 combination of Ni and Hi, theta A raised to the power Hi 1 minus theta A raised to the power Ni minus Hi, okay, raised to the power Zi into 1 by 2 combination of Ni and Hi, theta B raised to the power Hi 1 minus theta B raised to the power Ni minus Hi raised to the power 1 minus Zi. Alright, this is the expression. This expression will work because if Zi equals to 1, then the first factor remains and the second factor will becomes 1. Okay, this factor will becomes 1 and this will remain as it is. If Zi equals to 0, then the second factor remain as it is. Okay, but the first factor will becomes 1. Okay, so means we are going to choose the coin. It is coming from the coin A or coin B. So do you have any doubt till now up to here that we have done in this problem? Do you have any doubt, or should I proceed? So then for all experiments, the likelihood will be the likelihood will be theta B equals to the product of I goes to 1 to m, that is 5 basically, into 1 by 2 Ni Hi theta A raised to the power Hi 1 minus theta A raised to the power Ni minus Hi raised to the power Zi into 1 by 2 Ni. Combination of Ni and Hi, theta B raised to the power Hi 1 minus theta B raised to the power Ni minus Hi raised to the power minus 1 minus Zi. Alright. So this is, and after that we will take the log likelihood of this complete data. Okay. And we can find out for the MLE. So we are going to take the log likelihood of this one. Take log on both sides. Both sides. It will provide complete data log likelihood. log likelihood. Okay. So in that one, what we are going to do after this, so say log likelihood, we are going to denote with the small l, c, theta a, theta b. So when you are going to take the log likelihood of this function, what it will be? Summation I goes to 1 to m. The power will come in the summation, in the product basically, zi, okay, and apply the log inside. So it will be log 1 by 2 plus log ni hi, right, plus hi log theta a plus ni minus hi log of 1 minus theta a, okay, plus, so bracket will close here, then plus summation over the range of I goes to 1 to m 1 minus zi log of 1 by 2 plus log of ni hi plus hi log of theta b plus ni minus hi log of 1 minus theta b. Okay, so that will be your log likelihood. So that terms one log 1 by 2 and log ni hi will, they don't depends on the theta a and theta b, so they will not affect the maximization at all. So even though they are the part of the full likelihood function, so in that one, after that, we will go for the EM algorithm. Okay, now we will apply the, sorry, apply EM algorithm. So in that one, what we will do, we will compute the first E step. Two steps are there, so we are going to put the E step. So in this step, we will compute the conditional probability that experiment I use the coin A, given that the observed data and the current parameter, given the observed data and the current parameter values. So how we are going to define it? So we will define it as gamma I A is equals to probability that Zi equals to 1, means the coin A was selected for the given number of heads in experiment I, and for the given value of theta A, that is theta AT and theta BT. Alright, so this quantity is called as the responsibility of coin A for experiment I. Okay, so I just write it. So quantity is called the responsibility of coin A for experiment I. Alright. So we are going to use the Bayes theorem here. So by Bayes theorem, So because we know that the head is occurring, okay, but we do not know which coin was used. So if you remember the Bayes theorem, some examples that we do in the Bayes theorem, we says that we have the defective piece from each machine, say machine A, machine B, machine C, machine D, and we know that what is the percentage of getting the defective piece from each machine. And if we select few defective pieces from one particular lot, so what is the probability that this defective piece coming from this particular uh, machine, say machine A or B or C or D. So at that time we use the Bayes theorem. So that's why in the similar way we are going to use the Bayes theorem here, because we know that the head is occurring. Okay. And from which coin it is going to be occur, so that we need to find out. So here, so gamma I A will be basically the probability that Hi, this probability will be equals to Hi, given that Zi equals to 1 and with parameter theta A t at tth iteration into probability Zi equals to 1 divided by probability Hi, given that theta at and theta bt. All right. So when we are going to simplify this one, what will happen? Gamma IA will be equals to, what is this one? This one will be 1 by 2 into Ni Hi into theta A at tth iteration, okay, raised to the power Hi 1 minus theta A at tth iteration raised to the power Ni minus Hi, okay, divided by 1 by 2 Ni Hi theta A t raised to the power Hi 1 minus theta A t raised to the power Ni minus Hi plus 1 by 2 Ni Hi combination of Ni Hi theta B raised to the power theta B at tth iteration raised to the power Hi 1 minus theta B at tth iteration raised to the power Ni minus Hi. So here if you just see 1 by 2 and Ni Hi is common, that will cancel out here. So the simplified form of gamma I will be theta A t raised to the power Hi 1 minus theta A at tth iteration raised to the power Ni minus Hi divided by theta A at tth iteration raised to the power Hi 1 minus theta A at tth iteration raised to the power Ni minus Hi plus theta B raised to the at tth iteration raised to the power Hi 1 minus theta B at the tth iteration raised to the power Ni minus Hi. Right. So that is the basically form of gamma Ia. And then what will be the form of gamma IB? So gamma I will be 1 minus gamma Ia, because total probability of selecting a coin A is and coin B, total probability will be 1. So if probability of selecting coin A is gamma Ia, so then it will be gamma ib will be 1 minus gamma ia. So gamma ia basically the probability that the experiment I belongs to coin A based on the current parameter estimates. So this is basically a soft assignment rather than the difficult classification. So now we will go for the that one numerical portion of eth step here. Okay, this is the eth step that we got here. We just check it. What is the gamma ia will be? So we will assume that before going to that one, we are going to assume the value, initial value of that one, because that we need to do with the replication. Repetitions will be there. So we will take the initial guess. Take the initial value, that is theta a naught is basically 0.6. Assume that one. You are independent to choose the value. Okay, you don't need to be worried about that one. But that should be in the range between 0 to 1. Okay, and theta b at 0 iteration, it is supposed 0.5. Okay, so for experiment 1, we have h1 equals to 5 heads. So what will be gamma 1 a? It will be 0.6 raised to the power 5, because 5 heads are there, and 1 minus 0.6, so it will be 0.4 basically. 0.4 raised to the power 5 again, because 5 heads, then 5 tails, then 0.6 raised to the power 5 into 0.4 raised to the power 5 plus 0.5 raised to the power 5 and 0.5 raised to the power 5. So when you are going to solve this one, it will comes approximately 0.449. Means for the given current values of the parameters, that initial value 0.6 and 0.5, experiment 1 is slightly more likely to have the to come from coin A and then coin B, because at that time the probability of coming using the coin B is, it will be around 0.55 or 56. Okay, so that's how we need to do, and we need to do it for each experiment. So for first experiment, suppose we were getting 0.449 and 0.551 from here. Okay, so similarly we will repeat for second experiment, we will repeat for third experiment, we will repeat for fourth experiment, and we will repeat for the fifth experiment, and we get the value of gamma ia and gamma ib here. Okay, 0.8, 0.5, 0.734, 0.352, 0.67, 647, and so on. So after that, we will find out the expected number of heads from coin A. So what will be the total expected number of heads from coin A? It will be summation over the range of I, gamma I A into hi. That is the expected value. Okay, expected value of hi for given coin A. That is this one. Yes or no? And it will be 0.449 into 5 heads, 0.805 into 9. Okay, 0.734, into 8, and 0.352 into 4, 0.647 into 7. That will be equals to 21.29. That is the expectation. Okay, so that is the expected number of heads from the coin A. All right. So here we will go for the M step, maximization. Okay. So we have the formula for maximization is there. How we got this formula? So for that one, in the maximization step, we maximize the expected complete data log likelihood. So expected complete log likelihood is basically. Do you have any doubt up to here? Up to the expectation step. Do you have any doubt? Please let me know. Do you have any doubt up to here? Okay. So I just move further. So then the expected complete log likelihood is complete data log likelihood. That is your Q, sorry, Q, theta A and theta B. So that will be basically expected value of your complete data log likelihood that we defined here LC theta, LC theta A and theta B. This one, the expectation of this one, theta A and theta B. Okay, for the observed, given that the observed data that we have and the value of theta AT and theta BT that we have for the initial from the initial guess. Okay, at every and we know that here the expected value of Zi for given Hi is basically gamma Ia that we computed right now, and expected value of 1 minus Zi for given Hi is basically gamma Ib. That is the expected value of Zi and 1 minus Zi. So we get the likelihood expected value of that one QAB. It will be theta A and theta B. It will be equals to summation over the range of I goes to 1 to m gamma IA into Hi log theta A plus Ni minus Hi log of 1 minus theta A plus summation I goes to over the range of 1 to m gamma IB, okay, into Hi log of theta A, sorry, theta B plus Ni minus Hi log of 1 minus theta B. All right. Plus C, in the C is the constant terms, that is 1 by 2, and the combination terms, okay, that we are putting in the C. Okay, this is log 1 by 2 and this one log Ni Hi that we will put in that one in the constant term. So after that, how you are going to maximize it? Now we need to maximize maximize q theta A and theta B. All right, with respect to theta A. With respect to theta A, we need to maximize. So how we will maximize it? So now consider theta A. Consider the part where theta A is involved, because we are when you are going to how you find out the maximum. So you need to find out the derivative with respect to the theta A. So at that time this term will be 0. So only this term will be there. So we are going to find out the derivative of QA. Okay, theta A, that will be summation over the range of I goes to 1 to m gamma I A, okay, into hi log of theta A plus ni minus hi log of 1 minus theta A. We need to consider only this part. So find out the derivative with respect to the theta, partial derivative. So partial derivative of this one with respect to the parameter theta A of QA. So what it will be when you are going to find out the derivative? So gamma summation over the range of I goes to 1 to m gamma IA will remain as it is. Then when you are going to find out this derivative of this one, that it will be hi divided by theta A plus ni minus hi divided by 1 minus theta A. Then you need to find out the derivative of theta A. So it will be minus. So it will becomes minus that time, and put it equals to 0 to find out the to do the maximization. And now simplify this one, simplify this portion. So what it will be? It will becomes summation over the range of I goes to 1 to m gamma ia, okay, into hi into 1 minus theta a minus ni minus hi into theta a will equals to 0. This denominator part will go to the right hand side, so it will become 0. Now expand this one, multiply inside the bracket and expand this one. So it will provide you summation over the range of I goes to 1 to m gamma I. It will be hi minus theta a into hi minus ni theta a minus minus plus hi into theta a equals to 0. All right. So hi theta a will cancel out. So ni minus ni theta a will remain. So it will be summation over the range of I goes to 1 to m gamma I hi, sorry, yes, hi minus ni theta a equals to 0. All right. So now simplify it. All right. Multiply summation I equals to 1 to m gamma I inside the bracket and simplify it. So and solve it for the theta. So what it will happen? So summation I goes to 1 summation I goes to 1 to m gamma I hi minus uh, ni theta a into summation I goes to that one gamma I, sorry, gamma ia. So it will be summation over the range of I gamma ia hi minus summation over the range of I gamma ia ni theta a. Now solve it. So it will becomes, after the simplification, theta at plus 1 equals to summation over the range of I goes to 1 to m gamma I a into hi divided by summation over the range of I gamma I raised to the power gamma a into ni. This is the formula. Okay, this is the m step formula for coin A. So this is the m step formula for coin A. Okay. So now what we are going to do? Similarly, we will get for the coin B, that will be similarly for coin B theta bt plus 1 iteration, it will be summation over the range of I gamma IB into HI divided by summation over the range of I gamma IB into Ni. This is the formula. That's how these two formulas were derived. Okay. So after that, what we will do? First, m step numerical calculation that we are going to do. We are going to put the probability of success 0.449 that we got for the initial guess 0.6. Okay, and 0.805 into 9 plus 0.734 into 8 plus 0.352 into 4 plus 0.467 into 7 divided by 0.449 into 10 total number of observations plus 0.805 into 10 total number of observations and plus 0.734 into 10 plus 0.352 into 10 plus 0.647 into 10. So that will be 21.29 divided by 29.87. So that will be approximate to 0.713. And similarly for coin B, we will calculate here. So the probability was of the success was 0.551 into 5 plus 0.195 that we got from here. Okay, that we calculated here. 0.195 into 9 plus 0.266 into 8 plus 0.648 into 4 plus 0.353 into 7 divided by 0.551 into 10 plus 0.195 into 10 plus 0.66 into 10 plus 0.648 into 10 plus 0.353 into 10. It will becomes after the multiplication and summation, it will becomes 11.71 divided by 20.13, so approximately 0.582. Okay, so for the initial value you got, you started with the 0.600 and 0.50. Okay, but after this maximization you got the probability of for coin A is 0.713 and for coin B you got it at 0.582. So after that you will repeat it a number of times and till it is not going to be converged, and in the last you will find out that the probability after the replications every single time it is 0.797 and 0.520. Okay, so means theta A, the probability of success or probability of getting head from coin A is 0.8 and probability of getting head from coin B will be 0.52. Okay, so the algorithm converge monotonically, so likelihood never decreases here. So that is the basically example, mathematical example of EM algorithm here. Do you have any doubt in this one, or should we go for the R code? Do you have any doubt till now? Okay, so I just proceed with the R code here. I hope this is visible for all of you. Okay, So the two coin EM algorithm that we are writing here. So here 2 underscore coin underscore EM. In that one, we are going to define a new function. Okay. So that store the value here in that one function of data. The numeric vector that will it will be a numeric vector that will contain the number of heads observed in each experiment. Okay, this data set, and theta initial. Okay, that will be the numeric vector of length 2 for the giving the initial guesses for the probability of getting heads for coin A and coin B. And after that, we have the maximum number of iteration. So we are going to run it up to 100 iteration. And that in the tolerance 1 e raised to the power minus 6 means 0, it will be 0.0000001, means that is our convergence tolerance. That much difference we can tolerate. Only less than that means more than that difference we cannot tolerate. So this function will return a list containing the final estimates and the number of iteration performed and the history of the parameter values. Okay. So after that, vector of heads containing each out of 10 flips and theta initial. Okay, n flips. So we are going to flip the coin 10 times in each experiment. Okay. M is the number of M is the length of the data, means number of experiment. How many times we are going to repeat our experiment? That will be in the M. Okay. After that, we have the initial theta A. That is the theta initial with 1 and theta b with the theta initial 2. Okay, so these line extract the initial values of coin A and coin B from theta initial, and after that we have the history 1 comma that is equals to c theta and theta b. So in this one we will extract the initial value. Okay, this will create a matrix with a maximum iteration plus one row and two columns, and fill it the missing values as the MA. Okay, and it will store the parameter values across the all iterations. All right. Then because before that we are having the history, we are creating a matrix here, the null matrix. Okay, with the maximum iteration plus 1 and number of columns equals to 2. All right, and after that in that one the next history 1 comma m so it will initial values are stored in the first row of the history history matrix. Okay, so after that we are going for the em loop here. Okay, that will be the main loop. So this begins the em iteration loop, which will run at the most maximum iteration times. So whatever the maximum number of iteration times we are writing here, it will run up to that time. So in each step compute the responsibilities that we said. So like likelihood A and likelihood B, that will be the from the binomial distribution. So D binom will compute the binomial probability mass function for each coin and for each observed head in data, and it calculates the likelihood under the coin A and coin B. Okay, and then gamma A that we are going to calculate, that is the like A and divided by likelihood of A plus likelihood of B, and gamma B will be defined as the 1 minus gamma of A. All right. So this is the posterior probability that both of them are the posterior probability that will give the experiment come from the coin A or coin B. All right. And quantity gamma B, as we have discussed, that is basically 1 minus gamma A, because sum of two responsibilities are equals to 1. Okay. Then in the m step, what we are going to do here, we are going to define the theta a nu. Okay, that is the sum of gamma a into data divided by sum of gamma a into n flips, means total number of flips, and theta b nu, that is basically equals to the sum of gamma b into data divided by sum of gamma b into n number of flips. So these are the weighted maximum likelihood updates. So the numerator gives the weighted total number of heads, and the denominator gives the weighted of total number of flips. Okay. So here, after that, history iteration plus 1 equals to C theta A nu and theta B nu. So the updated parameter values will store here in the next row of the history matrix after the first one. So iteration will take the value from 1 to 3 up to maximum iteration. So because in the first one we are just taking the initial guess. So our whatever the estimated value of thetas we will get, they will started to store from the B. Okay, sorry, I'm saying B from the second row. Okay, now check the convergence. So in that one, if absolute theta A nu minus theta A is less than tolerance, and absolute theta B nu minus theta B is less than tolerance, then break it. Okay, break it, otherwise repeat it continuously. Okay, again repeat it. So the loop stops if both parameters change by less than the tolerance, that this limit. This tolerance limit, if it is going to be less than that one, then it should stop, otherwise it should again generate the value. All right, and the loop after this one convergence, we have the theta a that is equals to theta a nu, theta b that is equals to theta b nu, means here we update the current values for the next iteration. Okay, these values will use as a next iteration. So that we did here, the same thing we did here. We use these values 713 and 582 as the initial guess again. Earlier we took the initial guess 0.6, 0.5. After getting these values, these two, now we use the 713 and 582 as the initial guess, and again we estimate the values, and again we use, after that we got these values 0.75, 745 and 0.569. So again we used these values as the initial guess, and again we estimated it. All right. So after closing that one, we will prepare a list. So the function, it will return the final estimates of theta A and theta B and total number of iterations that we performed and the trimmed history matrix. Okay, from 1 to iteration 1. Okay, now after that, in this data set, we are going to use the data total number of heads 59847. So definitely we can easily calculate the total number of tails here. All right, but we need only number of heads. So initial guesses, we are giving that theta initial 0.6 and 0.5. Okay, and then we will run the EM algorithm. Okay, and in the result, two coin EM, that is the function. So we will give the heads data here and the theta initial value we will provide here. Okay, and it will contain the observed data, count of heads, and the initial values of the parameters. And then we will call EM algorithm results and theta A and theta B. Okay, up to the decimal point 4 for each one, and the number of iteration. Okay, so we just run it up to here first. All right, so this is the theta A, that is 0.79, and theta B is 0.5196. Here, if you just see, we had up to the 0.797 and 0.520. It will increase if we will increase the number of iteration. Okay, because we took the iteration here up to the 100. So, but it was converged at iteration 16, but we consider only the iteration up to the iteration 10 in the numerical example. Okay, for here, I just show the result up to the iteration 10, but it was converged in iteration 16. Okay, now we will go for the plot. So matplot, we are going to use here the command. Okay, so this plot will use shows that how parameter estimates evolve across the iteration, and the line iterate the convergence of the EM algorithm. Okay, so here what we are going to do in the result history, we are going to store the values of theta A and theta B, and we are going to use the line. And for 2, it should be color that we are going to use, that is blue and red, and in the x axis it should be iteration, and y axis it should be the parameter value. And the headline should be title of the plot should be EM convergence for 2 coin problem. And then we are going to apply the legend here. All right, so we just check it. All right, so these are the plots for theta A and theta B. So we started with the 0.6, and it started to increase, and it reached to the up to 0.8 somehow. And we started with 0.5, and then it was about somewhere between 0.51 or something. So it converged like this. Do you have any issue in this example? Okay. So now we will move to the another example, that is the two machine problem, that is for the continuous case. The previous problem that we discussed, that was for the discrete case. Now this is the continuous case. So here the scenario is like this. A factory has the two machine producing the ball bearings, and the bearings produced by two machines have the different average diameters. Okay, and however all bearings are mixed together before the inspection. Therefore, when we measure a bearing, we observe only its diameter, not the machine that it was produced. Okay, and now we just assume that whatever the machine one producing the bearings with diameters, so they are following the normal distribution with mean mu1 and variance sigma square, and machine 2 producing the bearings with diameters follows the normal distribution with mean mu2 and sigma square. Okay, so the hidden information is there. We observe the measurements, not but not which machine produce each bearing. So the machine identity is the latent variable here, Zi equals to 1 or 2, that we can assume here. Okay, so here we assume that machine 1 produce the diameter with mean mu1, and machine 2 produce the diameter with mean mu2. Okay, but both machines have the common variance here, sigma square. Okay, and suppose pi here denotes the proportion of being produced by machine 1. Okay, and the goal to estimate the parameter vector here in this question, say example 2, here suppose pi denotes the proportion of bearings produced by the machine 1. Okay, So the goal is to estimate the parameter value. Okay, so our aim or our goal to estimate the parameter vector say theta equals to pi mu1 mu2 and sigma square. These are the four parameters that we want to basically want to find out, estimate. So here suppose that the observed measurements are, okay, the observed measurement of the bearing's diameter is measurements are y1 y2 up to yn. All right, so for each observation yi we don't know which machine produced it. Okay, so to represent the hidden information, here we are defining the latent variable, say zi, that is taking the two values 1 and 2. All right, so where zi equals to 1, where it means that zi is going to take the value of 1 if observation I came from machine 1, and 2 if observation I came from machine 2. All right, so that will be the situation. And now if you just remember this thing, if one prefer the indicator notation, so they can define xi also. Okay, that is xi also they can take with the burn only, that xi equals to 1 if observation I came from the machine 1, or 0 if observation I came from the machine 2. In that case xi will follows the, or zi will follows the Bernoulli distribution with probability pi. All right, so here what we need to do, what will be the conditional distribution in this case? We need to compute conditional distribution. Okay, so measurements are assumed to follow the normal distribution. Okay, it assumes to follow the normal distribution conditional on the machine of origin. So we are assuming that it is yi given zi equals to 1 follows the normal distribution with mean mu1 with variance sigma square, and yi with, given that zi equals to 2, follows the normal distribution with mean mu2 and variance sigma square. All right, so again the machine's labels are unknown, so the marginal distribution of y is a mixture distribution. Okay, so how it will be it will be a mixture distribution in that case. Okay, the marginal distribution of y I is a mixture, as we have done in the previous example. So it will be f y I given theta, where theta having the all the parameters pi, mu1, mu2, and sigma square equals to pi phi yi mu1 sigma square plus 1 minus pi phi yi such that mu2 sigma square, right? So we obtain this formula in the similar way as we obtained in the previous one. Okay, like f yi given theta equals to probability zi equals to 1 into fy I given zi equals to 1 and theta plus probability of zi equals to 2 into phi, sorry, f yi given zi equals to 2 and theta. So from this formula we have obtained this one as we have done earlier. So here they have given us the 20 bearings diameter measurements that are given here: 2.1, 2.3, 2.0, 4.8, and so on up to 2.2 and 4.9. So if you just notice here, so we have the two clusters of values around 2.2 and 4.9. Some values are there that which are very close to 2.2, and which few values are which are very close to 4.9. So we if we see the binomial distribution, but we don't know which cluster each observation belongs to. So if we knew the labels, so simple group means will work here. All right. So here we need the EM algorithm. So for that one, the observed likelihood will be here the observed likelihood will be L theta for given y equals to product of I goes to 1 to n pi pi yi or with mu1 and sigma square plus 1 minus pi into pi yi with mu2 and sigma square. Okay, so this likelihood is very difficult to maximize directly because it is the product of two sums. Okay, and the EM algorithm will avoid this difficulty by introducing the latent information. Okay, and iteration between the estimating and the hidden variables probabilities, and it will update the model's parameters. So what we are going to do here, we are going to compute in the EM algorithm, we are going to compute the expected component membership probabilities given the current parameter values and maximize the expected complete data log likelihood using those probabilities. Okay, so the complete data likelihood will be here. We have apply EM algorithm and in that process we compute the complete data likelihood. So here we assume that let zik equals to is 1 and 0. Here if zik should take the value 1 if observation I belongs to the component k. Okay, and 0 otherwise. It should take 0. So here k is basically equals to 1 to 2, and then zi1 plus zi2 that we are introducing, that will be equals to 1. Okay, so in that case the complete data likelihood for one observations will be complete data likelihood for one observation is probability yi comma zi for given theta equals to pi into pi yi with mu1 and sigma square raised to the power zi1 into 1 minus pi into pi yi mu2 into sigma square raised to the power zi2. Okay, this is your likelihood, and for the entire sample it will becomes LC theta equals to product of I goes to 1 to n pi yi for with mu1 and sigma square raised to the power zi1 into 1 minus pi into pi yi with mu2 and sigma square raised to the power zi2. Okay, this will be your complete log likelihood function. Now take the log on both sides. This is the likelihood function. Now take log on both sides. So it will be LC theta equals to summation over the range of I goes to 1 to n z I1 into log pi plus log pi of yi mu1 and sigma square plus summation over the range of I z I2 log of 1 minus pi plus log of phi of yi, mu2 and sigma square. All right. So now use the normal density function here. Both of them are the normal distributions density function. So log phi is basically, what is the log phi y? I. That is basically minus 1 by 2 raised to the power log 2 pi, because what is the PDF of the normal distribution? That is 1 upon sigma root 2 pi into e raised to the power minus 1 by 2 sigma square x minus mu whole square. So it will be minus 1 by 2 log 2 pi minus 1 by 2 log of sigma square, okay, minus yi minus mu k whole square divided by 2 sigma square for all k equals to 1 to 2. So that is your likelihood log of density function. So now in the E step, what we need to do? At iteration T, define the responsibility of the component 1 for observation I. Okay. At iteration T, define the responsibility of component 1 for observation I as gamma I1 T is equals to probability that it is coming from the z I equals to 1 for the given data set yi into theta at the tth iteration. Okay, so now again use the Bayes theorem. So by Bayes theorem, okay, so it will be gamma I1t equals to probability of that zi equals to 1 into f yi given that zi equals to 1 and theta at the tth iteration divided by this pi at the tth iteration into pi, that is your normal density of yi, okay, with mu at tth iteration, mu1 at tth iteration and sigma square at tth iteration plus 1 minus pi at tth iteration into phi of yi, means the density function with the value of yi and mu2 at given at tth iteration and sigma square given at tth iteration. Okay. So that will be your each step, and here similarly gamma I2 T basically means it is coming from the second component, that is 1 minus gamma I1 at tth iteration. Okay, so gamma IKT is called the responsibility of the kth component for observation I. So this is the simple assignment probability. rather than complex cluster labeling. So here what we are going to do in this one, we started with the initial guesses, that is pi naught is equals to 0.5, mu1 equals to not equals to 2.5, and mu2 not equals to 4.5, and sigma not equals to 0.5, and sigma okay, yes, sigma naught equals to 0.25. So at that time, sigma square will be 0.25, and y1 we are considering as the 2.1. So we will compute the probability here uh, from the normal distribution with 1 upon root 2 pi into 0.25 e raised to the power minus 2.1 minus 2.5 whole square divided by 2 into 0.25. That will come as the 0.527. Okay. After this, we compute the 1 upon root 2 pi into 0.25 into e raised to the power minus 2.1 minus 4.5 whole square divided by 2 into 0.25. So that will approximate to the 0 that we are getting. Okay. So here what we are going to do, gamma 11 is equals to 0.5 into 0.527 from this formula. Okay. From this formula that we observed here. So pi t, that is 0.5 into pi values of phi I, that is 0.52 divided by 0.5 into 0.527 plus 0.5 into 0. So that is 1. So observation 2.1 is almost certainly come from the machine 1. Okay, that it is showing that. So we, after that we will go for the M step. Okay, so in the M step, what we are going to do, we are going to check the uh, effective sample size N1. That is basically the summation of over the range of I, gamma ik, and mixing the that one, mixing the proportion with pi t plus 1 at the t plus 1 iteration, that will be N1 divided by N. Okay, how it comes basically. So what is the N1 and N2? So N1 is basically summation over the range of I goes to 1 to N, gamma I1 T, and N2 is basically summation over the range of I, gamma I2 at the tth iteration. Okay, since the sum of both of them are equals to 1 for each I, so it will provide us that N1 plus N2, we are going to assume that is N. Okay, so from there we are computing using the mixture proportion, that is N1 upon N. All right, so definitely 1 minus pi will be N2 upon N. All right, so we update the mixing proportion. After that we will go for the update the means. That is basically mu k t plus 1 equals to summation I goes to 1 to N y I k into yi divided by N k. All right. So how it comes? It comes from the derivative of the log likelihood. Okay, we will take the relevant part of the expected log likelihood of mu k, and that is proportional to, basically comes after the derivation, that I'm not going to do the complete derivation here. Okay, that will comes like minus summation I goes to over the range of I, gamma I k at the tth iteration yi minus mu k whole square equals to 0. When you will find out the derivative with respect to the mu or sigma, so it will comes in such manner. So mu k will come after simplifying, it will comes like summation gamma ik into yi divided by nk, because we know that the what is the unbiased estimator of the sample mean, that is what is the unbiased estimator of the population mean mu when x follows the normal distribution, that is x bar, summation xi minus summation xi divided by the n. So from there it comes, but because we have the summation gamma ik here, so that will multiply here, multiply with the yi. All right, and this will gives us the weighted average formula, and the variance, the pulled that is called as the pulled variance. So it will come as the sigma t plus 1 square equals to summation double summation. First summation will go to k equals to 1 to 2, and summation I goes to 1 to n yi minus mu k t plus 1 whole square divided by n. All right, it comes from this one basically. So the variance appears in the Gaussian low density through like this: minus n by 2 log of sigma square minus 1 upon 2 sigma square summation over the range of k, and summation over the range of I gamma ik at tth iteration into yi minus mu k at t plus 1th iteration whole square. Okay, this is after we get after differentiating with respect to the sigma square, and we will put it equals to 0. So we get this formula. I hope you can get this formula if you already, because I already told you, this is your likelihood function. Okay, this is your likelihood function. You need to basically find out the derivative of this likelihood function. Okay, similarly as we have done for the that one binomial case in the discrete version. All right. So when we are going to iterate this one, so it is difficult to find out by hand because probabilities are there. So I just give the initial values of the pi here, that is 0.5, 2.50, 4.50 for mu2, and sigma is 0.5. So when I started the iteration, it comes like this: 0.5, 2.16, 4.91, 0.17, and so on. And after that, we have the R code for this one that we will do in the next class. Okay. If you have any doubt, you can ask me right now.